All right. So.
That's good.
All right. Okay, so we left off last class talking about measures of dispersion or variation, specifically the variance and the standard deviation. Here was kind of the equation that we had, worked through it, a bunch of different examples. I believe where I left off was we didn't go through any kind of examples, kind of work through some on your own. You'll have some in that connect homework assignment that you'll have to do similar to this. So I'll kind of walk through, we'll kind of start out and see if, and I'll talk through it a little bit and then we'll come back to this. So hopefully everyone's able to kind of get on that AA frequency or kind of link up with the app. But remember what we said, we wanted to find a population variance. There you go. We're going to go through every single observation. We're going to subtract the mean and then square that deviation. We're going to do that for every single observation and then add them all up. And then finally, we'll divide by the number of observations that we have. Right? So that's our population variance equation. So I'll give you a little bit of time to kind of work on this. You can work with each other, people next to you, and try to come up with what your variance is. I'll probably give you about a minute and a half or so, 2 minutes, and we'll kind of talk about some, how we work through it. So you've got a small data set, you have 7 observations, right? Go through from the deviation squared for each observation, add them up, and then you'll be dividing by the number of observations. And I gave you the mean here, so you don't have to calculate that. I might find out today. So when you use these eye clickers, it'll help to have like a calculator or a computer or something in front of you.
This is the standard deviation square. Is that what you were? Oh, just that's an answer. I think submitting.
And I think you'll have to round to the nearest integer. So give you about another 20 seconds here at the 4-minute mark and
I did it without the equation. I was so proud. I was really scared. I thought I didn't want it on my calculator. But you
All right, if you don't have an answer in, take your best guess with where you're at kind of in your work now. I think there should be 11 of us. 2 more of you. 1, 2, 3, 4, 5, 6, 7. Everyone's got an answer in? So I think there should be 14 of you. 1, 2, 3, 4, 5, 6, 7, 9, 10. Okay. All right, I'm going to close it out. There we go. Let's say one of you was straggling. We'll go over this in a second, but I want to ask one more question just to kind of see where our understanding's at. Which of these answers, I'm going to give you like, not very long on this one, 15, 20 seconds. Which of these answers can you rule out right away just by looking at the values in the data set? So respond with which of these. If you put an answer in that you thought was right, you shouldn't put that again, right? I want you to answer which of these can you rule out right away just by looking at these 7 observations values. All right. Put your best guess, your response to those. Still need 3 of you, so make sure you're putting which one of these. All right. So, first of all, which of these can you rule out right away? Why?
There's not a single data set that's zeros.
There may be. We never wanted to say it'll never happen, but any interesting data we have, in order to have a variance of 0, it would have to be that every observation had the exact same value. So we're thinking about the equation for the variance. I'm going to give you one more way to think about it. I don't think I said last class. When we think about when we're taking an average, remember I kind of walked through and showed you how you can really think of it as though every observation is carrying the weight of 1 over the number of observations, right? We can pull that 1 over n out in front. So when we're finding a mean or an average, we're trying to find the middle of this variable x, the middle value. What we're doing here is you could still kind of pull that 1 over n out, and our variance is really measuring the average, not just x variable, but the average deviation from the mean squared. So some variables are going to be evidence that we're further, that there is more variation. Some is going to be that there's none. And our variance is really kind of finding the average of that deviation from the mean squared. Right? So in order for it to be 0, it would have to be that every single observation provides evidence that there is 0 variance from the mean, which means every observation would be exactly equal. So first question was, what is the actual population variance here? So we can rule A out, but then we have to kind of do some work to figure out the next 3. So probably the easiest way to do this, I think, is just to set up a column right next to the data. Take your x value of 20, subtract that mean of 45, it's what, negative 25, square that value. Then take the next value, 35, subtract the mean of 45, that's negative 10, square that, that's 100, write that value down. Do that for every single one of these 7 observations, then add them all up, right? You get 2,900 if you add up all those deviations squared. But we're finding kind of like the average deviation from the mean squared, so we have to divide by the total number of observations. So there we get a population variance of 414. Any questions on that? So sometimes I like to give you a little bit of time to work on these. If you run into a problem or something, like, feel free, please ask me about, like, I got stuck on this part, or why was I getting this wrong, or getting this answer wrong? So, do we have no questions? Okay. Oops, I already showed you. We won't use this one since I already showed you. But what if I ask you to find the sample variance here? Right? I said, oh, you know what? I told you to find the population variance, but this actually wasn't population data. It was actually only sample data. What should happen to your variance? Either one, yeah.
Like you would do the 2,900 divided by 6.
It's the same data set, so we're going to get the same exact values. We're going to get that 2,900 in the numerator. The only thing that changes is if it's a sample data set, we divide by n minus 1. So we're going to be dividing by 6 instead of 7, which should do what? right? If we did this calculation, instead we divide by 6, what should happen to this value? Should be higher, divided by n-1, errors on the side of caution. The only answer here that's higher would be C. I didn't open this one up, but this, I think we did have a question. Okay. So not too bad. So one thing we didn't get to last, did I show you how to do like the mean, median, and mode in Excel last class? Okay, I thought that's kind of like where we ended, right? Yeah. So I've got you guys, I have a regular stats section Monday, Wednesday, Friday, and then they gave me a stats that only meets Monday, Wednesday. So like I'm always at different points, it's starting to really get to me. So I think I also grabbed new markers that decided that they are like not dark and don't want to work. So I'll try to do a good job of this, and then I'll use the slides up here. So if we have some distribution, remember when we did these frequency distributions, so let's say it looks something like this. Right? I'm going to draw it as continuous instead of a bunch of rectangles just to kind of this. Remember, each point of this like distribution is telling me the frequency of different responses for this x variable. So let's say I have mean of 50, and the variance of this distribution is also 50. Okay. Then I have a different distribution, second distribution. Its mean is also 50, but its variance is higher. So if it has a higher variance, what that means is the data is more spread out. The average deviation from the mean is much larger. So what's going to end up happening, right, is this second distribution, because it has a higher variance, the values that are close to the mean are going to become less likely, right? This is kind of, these values are becoming less likely because there's more variation in the data, which also means that values that are further from the mean are going to become more likely, right? Remember, these are representing frequencies, so more likely or more frequent. So as we have, go from the black to the red line or black to the red distribution, if our variance is higher, that actually means we have a flatter distribution, a flatter curve, because it means the data is more spread out. But it's more likely we see values further from the mean, less likely we see values right around the mean. And then vice versa, right? If I went from a higher variance to a lower variance means that the values around the mean are more likely. So I'm going to end up with this higher peak distribution. And we kind of have that same thing going on here, right? Going from the blue all the way down to, I think it's like a gray. I'm going to higher variances. So the higher variances mean the data is more spread out and it flattens those curves. Whereas if I go to a lower variance, it's kind of peaking that curve, right? Making the values right around the mean much more likely. So changes in the standard deviation or variance, right? They're one and the same, just scaling the variance to the standard deviation. As we see a higher variance, we're going to get a flatter curve, or lower variance and more peak. A change in the variance is going to change kind of like where the middle part of our distribution is at on the y-axis. The lower the variance, the more peaked, right? The higher it is on the y-axis. The higher the variance, the flatter it is, or kind of the lower it is on the x-axis there in the middle of the distribution. What happens if instead, I'll go over here. What happens if I've got two distributions and they have the same variance, but one of them, not Lou, 100, has a higher mean, right? So let's say we start out, I've got this distribution, and it's got a mean of 50. If I have instead the same variance but a higher mean, what's that going to do to my distribution? Should just shifts my distribution, right? So the variance was changing kind of where I was at on the y-axis. I mean, it's kind of not exactly said correctly, right? Because it's like kind of, is it more peaked or flatter, but it changed kind of the height or the y-axis values of my distribution. Whereas if I had the same variance, and I try to draw these the same, looks like I didn't quite get it. Right? It's going to have the same shape, same height, but a higher mean or a lower mean just shifts me along the x-axis. Okay? So just knowing things about the mean and the variance of a data set, we can start to compare kind of distributions across multiple data sets. Right? We know that difference in means will just shift the distribution, difference in variances will kind of change how peaked or flat it is. Any questions on anything related to that before we keep moving? Okay, so we did this last class. None of this is terribly tough, right? They're built-in functions that do all the work for us in Excel. So that's kind of nice. I did get up that first Excel homework. You have to do some descriptive statistics, build your own frequency distribution, do some time series, and do some kind of playing around with some things in Excel, just some general like critical thinking. I might show you something at the end of class today. If we don't get to it, I'll definitely do it on Friday, where I just show you how to kind of utilize the filter tool on Excel. I also have that, all the work we did in Excel, like pasted into one video. It might not all be from this class. I kind of took some pieces of things I liked more from different sections, but for you guys, I made sure there's everything that we kind of could have covered. Okay. All right. Any questions for me before we kind of move on to the next topic? Okay, so I filmed a video for this, and then we're going to probably cover it today. So I might think what I'm going to try to do. I'll probably try to do a pre-class video over the weekend from Friday to Monday that I expect you kind of watch before we start class on Monday. But I might post the one that I did on weighted means just because it's a different way of hearing it spoken about. I'm going to use that for my I didn't plan on using it for you guys, but I'll put it up there just so you have an additional resource. But we're going to change topics a little bit and kind of building on what we've done, but it's a little bit of a new way of thinking about data. So when we calculate a mean, and I already referenced this already, but we said we can really think about this as we're going to be doing something like this, right? Where you can really think about it as though we're trying to find where the middle of that middle x value is. Each value is going to carry the same weight, just one out of the number of observations. Well, that's if we have like I guess I don't want to say a normal data set, but kind of a typical cross-sectional data set. Sometimes we're going to have something that's a little bit different, right? So sometimes we might see something like, and this is, I think I used the same example in the video. I really like it, so I'm using it again. So let's say that for whatever reason, I can only see the average grade of different level like classifications, right? So I got this class, and I know that the sophomores in the class have a really low GPA. I don't know, maybe the juniors are a good group. Wait, you guys are sophomores, right? Most of you?
No.
There we go. No, I like the group ahead of you, though, so I couldn't think of anything. But and then we have kind of the seniors down here. And let's say they're kind of somewhere in between. Right? Well, typically, if you want to find the average GPA, you would just add these numbers up, divide by 3. But the problem is, what if I'm seeing the average GPA of all sophomores, right? But let's say I only have 10 sophomores in the class, whereas I have something like 40 juniors. And then maybe, actually, yeah, we'll do this, right? And then maybe I have 50 seniors. Right? So my class is kind of not near as many sophomores, even though that's the group that has the highest GPA. So when I'm thinking about if I only have group data is given to me or presented to me where I only see like the group averages, well, I know that there's 100 students here, right? So one way to think about this is out of the 100 students, how many of them are sophomores? 10 out of 100. Right? So instead of every observation carrying the weight of 1 over n, now they should really only carry the weight of whatever proportion of the data they were. And we could see every individual student, each student was just 1 out of the total, right? But now when we're looking at these GPAs, this GPA represents 10 out of the 100 students. So we're going to use that kind of as our weight, multiply that 3.5 by that weight, and then add to that the next group, which is 40 out of the 100, times their GPA, right, or their value. And then the last group, the proportion that they make up of all the students times their GPA. So we would call this a weighted mean, right? We're really only using 3 values to find this mean. It's just that we have to weight them appropriately because we know this 3.5 should carry way less weight in calculating the average over the entire class because there's only 10 students. It only represents 10 students. Whereas that 3.0 represented 50 students. So that's one way of thinking about it. The other way of thinking about it is a slightly different kind of, but we'll keep going. So I used to use this example of like fast food sales, and maybe certain fast food represent a higher number of companies, and so we can't just take the average over all of them. I don't like that example anymore, and I guess I haven't changed it from the slides, and I just come up with an example that I like in class. So the equation we could also use is this guy right here. So that's one way to think about it, using like the proportion out of the total that each one represents. If instead I had written it this way, where I go through every observation, I take the x value and multiply it by its weight, where I'm using the number of students simply as the weight. Right? And then at the very end, I then divide by the sum of the weights. Well, notice if I do that, I've got what? The very first weight would be 10 times that GPA of 3.5, plus the second weight would be 40 times their GPA was, no, they were the dumb ones, right? 2.0. I probably shouldn't say things like that, but these aren't real people, right? So the third group, right, had 50 people, and they were not 3.0, they were 3.5, they were 3.0. That would be my numerator, right? And then I'd be dividing by the sum of the weights, so 10 plus 40 plus 50. But notice I could actually rewrite this, right? This is just 100. Everything's being divided by 100, so I could just pull out 10 over 100 times that 3.5 plus 40 over 100 times that 2.0 GPA plus 50 over 100 times that 3.0, right? And I have the exact same thing that I have over there. So it's just a different way of thinking about it. I think this equation is just a little bit easier to like, if you've got the frequency and you've got the variable there, it's just easier to like multiply across and then add them up. And so that's usually why we think of the equation being what it is up here. But it helps you to like think about, well, what's their proportion of that observation out of the total, right? So 10 out of 100, 40 out of 100. You could think about it that way as well. And that kind of links up a little bit more so with like what we were doing with the original. So, I think probably the easiest steps is not doing it the first way I showed you, but instead doing it the second way. All right. So, our class is just taking all kinds of turns today. So, just multiply each value you have by its weight, right? So that would be like cross multiplying, right? Take the 3.5, multiply by 10, 2.0, multiply by 40, so on and so forth. Then add them all up, right? So sum up all those products. Then add all the weights together, and then you would have two numbers. Just take your numerator, divide it by your denominator, or divide the sum of those products by the sum of your weights. Okay. Any questions over any of that? Shouldn't be too terribly bad. So you can go out and grab income data from the census, but you can't get like an individual. I think you can like, I don't know, put in a proposal and get like individual level data. But if you're just grabbing it kind of from the public data, you have to grab it based off of different groupings, right? So for instance, what do I have here? I got income data from the census broken down by race and gender, right? You can do some socioeconomic things, you can do some region things, which I'll show you in a second. But these are two of the other options they have. So here, right, you can kind of think about, I'm going to look at overall mean incomes for men and then overall mean incomes for women. The problem is, I've got it kind of broken down. It's killing me.
I think it's on the brush. We can just pull it up.
That might be the way we have to do it. I don't know why it keeps going up. I was told a long time ago that when they put these things in the wall, that they're actually like did a really bad job of it, and so sometimes the HDMI's can't go in all the way. That's why I think before I got it to work, because I was just messing around with it. Oh, Christ. True. All right, there we go. So I only have the data. We don't talk fast. We've got the data broken down by each racial group, or at least the way that the census records it. Obviously, this the 4 groups is somewhat, presents other issues we could talk about. But for the way they display it, we've got the average income for these different groups. However, if we think about the demographics of the U.S., there's going to be a much higher percent of our observations are going to come from white individuals versus Hispanic or Asian. So, we have to factor in that each one of those mean incomes represents a higher or lower number of people, right? If we want to find the overall average income for men in the U.S., right, regardless of race. So, what process would we do? Right? Well, I've got my variable that I'm interested in finding the mean of. Income. I've got income for 4 different groups, and each one represents a different number. So I'll go through, I'll take the X value, multiply it by the weight of that group. Add to that the next racial group's average income times the weight for that group. Do that for each one. So once I add all those up, I then divide by the sum of my weights. Where my weights here, I was using the number of individuals in each one of these racial categories. Each one of these race categories. So I've already given you that total. I actually already added the weights up for you. So we got it there. And really the rest of it's just a matter of kind of putting these things in, right? Take all those products, the 4 groups, add them up, and then divide by the sum of our weights here, which if I didn't give you the total, you could have done on your own. Or since I had it up here in the graph, just use that 180,000. So you can do the same thing for females. Might be a good practice if you're like having trouble with these weighted means. Try to go through and do the exact same thing for females and reproduce this value, right? So this is a quick snapshot, but it's kind of this is old, a little bit older data, but it's also kind of like sad. Like you see the disparity across not only gender, but you also see disparities across race. You would wish that you would look at this and see that they're a little bit closer, across these dimensions. But this is the actual data from the census, so kind of interesting. You kind of quickly realize that there's disparities on several axes here. But we can calculate that average, weighted average for income pretty easily, especially if it's only 4 groups. It's not too terribly tough. Is this making sense? Is there any questions on this? It shouldn't be too bad. It's a little bit trickier if we want to do things with variances. So before we get to that, if I was instead, I have it broken down now by gender and region of the country. So notice like the South and West have a little bit lower incomes. So which one of these groups is going to influence the mean the most, whether or not we're doing the average kind of weighted mean for males or weighted mean salary for females?
Would it be females in the South?
So if I was trying to calculate, I'll clarify my question. If I was trying to find the weighted mean salary for men, which one would it be? South, because why? Because the highest weight, right? The highest frequency, right? What's more interesting is if I want to find the overall average salary, right? So across males and across females, what would I do there? I don't have this in the slide. This is a good thought experiment. And you're right. If I was doing it across men and women, the one that would influence the most are women in the South. That income would take over the most because that's the group where it represents the highest number of individuals. So if I wanted to find the overall weighted mean, I'd have, instead of 4 groups, I'd actually have 8 groups. And I would just have to go through, take the weight, multiply by the x value, plus the next group's weight times its x value, plus the next one, and then go plus this one, right? Plus this product and this product. And then I would divide by the sum of my weights. Well, now the sum of my weights would be these plus these, right? So yeah, you could do that as well. Right? I don't have it up here, but you could easily kind of went across both. And the idea here is that whatever has the highest weight, and here the highest number of individuals, our weights we'll see can end up being different things. But that's going to be one that influences the weighted mean the most. Okay. So we can also do a weighted variance. It's going to look pretty similar to what we're doing with our regular variance equation. It's just that we're going to have kind of our deviation from the mean. Well, each observation will have a deviation from the mean, but we need to weight that, right? Because it's no longer should be weighted 1 out of n, it's whatever that weight is. And so there in the denominator, I have a capital N, let me see. So you could also write it like this for a weighted variance. All right, using the sum of the weights. So this is kind of a weird idea, but given up what we were just talking about, if I add up these weights here, that was just everybody in my sample or everybody in my population, right? So when I'm adding up the weights, it's the same thing as saying divide by whatever the original total number was in the population, but it's a little bit, you're never going to be given that directly. It's like if I could observe the original data where I had every individual's income, then yes, I'd be dividing by the total number of observations in that data set. The problem is if I'm doing a weighted mean or a weighted variance, it's probably because I can't see the original data, right? So instead of having n, I'm probably going to have to figure out what that is by adding up my weights. Questions on this? So I'll show you an example. So if we use kind of just the male data to find the variance in males, male income, right, across these groups. So I would take that income for this group, subtract my mean, which my mean was what, 53,000 or something like that, square that value, and then multiply it by 73,000. Write that number down. That's the deviation squared times the weight. Right? Now you can see when I'm dealing with income, these numbers become very large pretty quickly, right? So this is kind of a pain. I don't give you examples like this on the exam or anything where you're having these ridiculous of numbers, but this is the process you use. So then you go to the next income, 38,000. Well, that's further from that mean of 53. So when we square that, right, that would add a larger amount to my numerator, but it doesn't represent near as many people. So when I take that deviation, right, 38,000 minus 53,000, and I square it, I still have to multiply by the weight. So now notice, even though it was a much larger deviation, it really is only adding a similar amount to that numerator because it represented way fewer people, right? And our weights are now being factored in. I then do the same thing for the next 2 groups and then add them all up. That's my numerator. Final thing was divide by n, where I said here, really that's the sum of my weights. So here I'd be dividing by sum of my weights. And so take that 94,000. Oh, wait, maybe that's already, sorry. add these up, divide by the sum of the weights, and you get 94,000, sorry. Right? So it didn't show that the additional step, but if you added these up, divide by the sum of your weights, that's how we're getting that variance value. And you could reproduce this for females as well. Notice much lower variance in female income than there is in male income based off this data, like quite a bit lower, which is kind of interesting, but really it's being driven by, like, we're not seeing this extremely high incomes in any of the female groups. So that's really what I think where that's coming from. But you could try to work through this similar example with female income and come up with that weighted variance as well. Yeah.
So sorry, but what is the variance, what is that representing?
So on unweighted variance, like the ones we were talking about before, I would say a good way to think about it is it's measuring the average deviation from the mean across every observation. Okay? So it's kind of like, on average, how much does the data vary from its middle point? Another way. So with a weighted variance, it's the same interpretation. It's just we're basing it off of group data as opposed to like the individual level data. So it's still measuring the average variation we see, but here really it's the average variation we see in income really across whatever groups we have it grouped in. Here we have it grouped by race. So it's the average variation we see across in income across races here, right? Or if I did it with the other one, if I was coming up with weighted variances for this one, the weighted variance represents the average variation from that mean we see across regions, right? So now instead of overall, because we don't have every individual, right? We've got group data. It's the average variation from the mean across whatever it's grouped by. Does that make? Okay. I think I even have the numbers. You could recreate these for region as well. I just kind of put these in the slides so that you did want to do some extra work to make sure you understand how to do this by hand. You can kind of use this data and you have the answer so you know what you should be getting. Hopefully you can reproduce these values. So notice even when it comes to region, not just race, females, there's much less variation, right, across region and race than males. But there's also much less variation across regions than there are race, which kind of makes sense given that when you know anything about the social issues related to that. So just a couple different examples of the same thing. How much time we've got? Well, we'll keep going, I guess. We'll do this. It's not that much more interesting, I don't think, but it's just something that or issue that we might run into is that when we're dealing with group data, sometimes I won't have like a specific value. So maybe like if I wanted to do income and like how many people make, exactly this amount, I could do that and then say, okay, that there was 50 people making exactly $32,451, but it's more likely I'm going to present the data to you in bins, right? This many people make between 40 and 50,000, this many people. So a lot of times we'll have responses for the variable X that we're interested in, but we're going to be presented the data in bins, right? So here, there was some survey given over, the satisfaction rate, I believe, I remember it was right, the data, this data set was like some product, how pleased they were with the product, right? Well, 4 people responded with some value in the range of 36 to 38, 15 responded with a value of 39, 40, or 41, so on and so forth, right? Like I said, you can imagine we could see this data presented. Here's the distribution of the frequency of people in each one of these income bands, right? Well, if I want to find the mean satisfaction rating, one problem is I don't have any specific X values, right? I just got these ranges. So if we're ever given data like this or grouped data like this, we'll just use the midpoint or the median of those ranges, right? So what's exactly in the middle? So for 36 to 38, we use the value of 37. 39 to 41, we use the value of 40. 42 to 40, we use 43, so on and so forth. So we'll take the midpoint of our bins, and then we'll use these frequencies as our weights, right? Because that value of 43 kind of reflects 25 individuals, while the value of 37 only reflects 4, right? So it should be carrying a much smaller weight. So if I'm looking at this data, just thinking about what we're doing with weighted means, what do you think is what statements would you maybe be able to make about where the mean is, where the variance or standard deviation is? If you had to guess what the mean of this data set is, what would you say? Yeah, right. It's the most frequent, or the thing that's going to be weighted the highest is that value right in the middle at 43. There's about equal number of observations that are 2 above it and 2 below it, and then very few observations that are very far. So yeah, it's probably going to be somewhere in that range of 42 to 44, right? If I had to guess. Maybe a little bit higher, right? It was 19 instead of 15 that are above it, so maybe it could pull a little bit closer up to 44. What do you think is going to be true about the variance? Especially compared to the last data set we're looking at, it's going to be relatively small, right? I mean, the range is very small, right? 49 to 37 midpoint, the range is pretty small. So we're probably going to have a pretty low variation as well. Also, the majority of the data is kind of centered there in the middle. The observations, or the values that are further out represent a very small number of people, and so they shouldn't influence the variance that much. So we can go through both. We can find this mean, and really it's the same thing we had before. It's just we have to use the midpoints as our x values, and our weights, well, they're still weights, it's just their frequencies, right? It's a number that we're going to see in each one of these bins. And I'm going to divide by the sum of my weights, which now we're just using the frequency, so it's just a little bit of notation change. And the sum of those frequencies should be the original size of my sample, right? If I add these frequencies up, right? Remember when we were doing frequency distributions, we said if we add the frequencies up, we should get the total number of observations. Same thing. When we're presenting group data like this, and we're given frequencies, we know that if we add the frequencies up, it's the same thing as going to be our sample size. So we can notate that either way. In practice, we're going to have to add the frequencies up. So that's why the first equation is going to be the one that we actually use. And then I want to do the variance. Same idea. I'm going to take the midpoint deviation from the mean squared, and then I have to weight it by its frequency. When I add all those up, if I'm doing a sample variance, I'll do n minus 1, remember, where n, I can't directly see it, but I can come up with n by taking the sum of the frequencies. So I could rewrite this right next to it if I wanted to. And remember this denominator, really I would take the sum of the frequencies minus 1, right? But the reason why we would do that stems from the same idea that we really are, if it's a sample data set, should be divided by n minus 1, or the sum of the frequencies minus 1. So we would go through this one just to kind of see what we're kind of walk through it together. I would take, did I not find the average here? So I'm going to use my equation for finding the average. I'm going to go through each one. I'll take the midpoint of 37, multiply it by 4, write that number down. 40 times 15, write that number down. Do that for every single observation. Now I've got kind of my frequencies multiplied by the midpoint of each bin. I'll add all those up. Right, so I add all those up, I get 2,795. So that's my numerator. I'll then divide by n, or divide by the sum of my frequencies. Here I don't have n, well I do, but I have to calculate it. By adding up my frequencies, right? So if I add up all my frequencies, I get 65. So I divide by 65 there. Okay. Any questions on that? Like I said, it's kind of like stuff we've been doing. It's like really similar to the weighted variance, really similar to or the weighted mean. It's just we're using midpoints and frequencies instead. So to then find the variance, right? I just take my midpoint of 37, subtract 4, and we said it should be between 42 and 44. Sure enough, it's exactly 42. Okay. So to find the variance, I'll take that midpoint of 37. It's deviation from that mean of 43. So 37 minus 43 is what, -6. The frequency is 4. So I multiply. Oh, sorry. I square that -6, right? The deviation from the mean, I then square that, right? So 36 and then multiply by 4, I get 144. And the next observation, its midpoint is 40. Subtract the mean of 43, so 40 minus 43 is -3. Square that, I get 9. Multiply by its frequency of 15, 135. This middle one, the midpoint is 43 minus the mean of 43 gives me, well, 43 minus 43 is 0, square root is 0, multiplied by 25, well, anything times 0 is 0. Right? And so on and so forth. We'll then add up all those deviations squared times their frequency. And here, if this is sample data, instead of dividing by the sum of my frequencies, I will divide by the sum of my frequencies. Oops, my little top thing's in the way. -1, right? So instead of 65, I redivide it by 64. All right, so I think we'll start next class out with percentiles, but if you have any questions about the weighted variance or weighted mean, feel free to reach out. Went through a little bit quicker than I usually do, but I will get that video up there. It walks through a very similar idea that I was doing here. It's just I make it a little bit more slower in the way I'm describing. It might be a little bit easier to follow. So look for that on YouTube. Other than that, if there aren't any questions for me, I'll see you guys on Friday.